Okay, so today's topic is um, Rockset is acquired by OpenAI, right? That's a news like month and a half ago. What's next for its users? So this webinar, we're going to provide a high-level useful guide for Rockset users. What you should do from now on and what are your options, right? Now let's get started. So let's first take a look at the agenda. So first, we're going to talk about the acquisition itself, right? Very briefly, why they do it and some speculations. And then we're going to talk about timelines for Rockset users and immediate actions and what you should do like right now. And then we're going to dive into two of the Rockset use cases and Rockset's own strength and weaknesses in those two use cases. So strength, your next solution is going to try to match those strengths at least. And weaknesses are, Rockset is closing. It's probably opportunity for you, to move to a solution that can address, those pain points, right? And first, we're going to talk about hybrid search briefly. And then we're going to focus on dive a little deeper into real-time analytics, SQL, OLAP, right? And then we're going to talk about top alternatives for mainly real-time analytics, pros and cons for each one, and what to consider when you make your choice. Okay, now let's get started. So OpenAI acquires Rockset, right? On their website, it says, we will integrate Rockset's technology to power their retrieval infrastructure across products, and members of Rockset's world-class team will join OpenAI. So the acquisition is mainly about their Rockset, their cloud-based solution, right? And OpenAI is probably going to use it for retrieval augmentation, RAG solutions, right? And also, it makes sense for them to acquire Rockset as well, right? For their own data infrastructure. Rockset's original team is the team behind RocksDB, right? Facebook. And also, they have a bunch of initial contributors for the Hadoop project, and they have a great engineering team. And they build a great product, Rockset. And this is really a surprise, but it makes a lot of sense. OpenAI would acquire them. So congratulations to the Rockset team first. And then let's take a look at some timelines, right? So this is straight out of Rockset's own blog or website, right? So the key thing here is a date, September the 30th, which is around a little more than 2 months away, right? Even your paying customers, if you don't have a contract, your server will be off in exactly 2 months, right? So now is absolutely the time for you to get moving, because for a solution that's similar to Rockset, a data infrastructure level, software, it takes time to build your POC and to consider different solutions and to do the migration, right? And to make sure that everything's stable, shadow traffic, and that whole thing probably takes, 1 to 2 months, right? If you do it fast. So now it's really the time to move. So first, you want to assess your current usage and requirements, right? What you're looking for your next solution. And then you should start make a list of alternative platforms that offer, similar or even better capabilities, right? And then you need to begin planning the migration process, right? And also to run, your new solution besides parallel with your Rockset cluster. So make sure that, new solution is stable, right? And to avoid any disruption to your operation, right? So now let's actually get started into the main material today, Rockset use cases. So first, we want to talk about hybrid search, right? So hybrid search or vector similarity search, or those RAG applications, it's actually a pivot that Rockset did around a year and a half ago, right? So before they were a kind of like a real-time analytics solution, right? And they see their architecture is more suitable for a search, a hybrid search kind of scenario, and that's when they make the pivot, and it really makes sense, for me. And Rockset at space is RocksDB, right, with different kind of indexes to support different kinds of workloads, right? They just added vector index, so ANN indexes like phase or HNSW, right? To support vector similarity search, right? And they have inverted index, BM25, those to do text search, right? And geo search and point queries because they have a row index, to row store index, it can run really fast point queries, and also a columnar store index to run analytical queries. So at hybrid search, this is really important for all kinds of different search use cases, right? Let's just say for vector similarity search. Vector similarity search is basically you use a kind of a machine learning algorithm or a deep learning algorithm, right? And you embed your higher dimensional unstructured data, let's say image, right, into a vector that's linearly separable, right? Linearly separable meaning you can just compare the two with the distance function, right? And not all of the data can be processed by a machine learning algorithm and become linearly separable, right? So you need other types of workloads, and this is why other types of search, to facilitate your vector similarity search and do all of them together, and then come up with a solution, right? And this is why hybrid search is very important. It's a very important use case. And Rockset, by its core, relying so heavily on different kinds of indexes, it's great for this kind of workload, right? So what you should consider, right, when you look for your next solution for your hybrid search or vector similarity search, or those kind of workloads, right? So first, you have to consider the type of data that needs to be searched, right? Is vector by itself enough, or you need to have other things we'll just talk about, right? And that affects the kind of solution that's available to you, right? And also you have to consider the number of vectors that you have, and also the concurrency, latency, and recall requirements for a similarity search, right? And I don't know what workloads you guys are running on top of Rockset in terms of search, but we see a lot of RAG application for LLMs, right? But there are actually a whole other set of search or vector search kind of use cases before LLM, right? All of the vector databases you hear about today, like Milvus, Pinecone, or Viviet, right? They were built before LLM. So, there are just a huge variety of workloads out there, right? Not RAG. So I remember I was working with a client, they were a self-driving company, they built algorithms for, self-driving, and they were trying to use a vector database to label their data set, right? Videos, so images in videos, and that's in hundreds of billions scale, right? Just so many vectors, right? That requires scalability, right? And I also worked with a user that is like, they're building a recommender system, right? To recommend kind of like tweets to the users that are, near them, right? They have a lot of users. So, but the vectors, a vector base, for each user to search through, it's not that big. But their QPS requirements like 30K, 30,000 searches per second, and that is very different than where you would from that self-driving company, right? And for this 30,000 with very smaller data set, actually, and they end up using GPU, right? And for this use case and that use case, it's really different. What kind of vector database you should go for, right? And absolutely consider those metrics when you research for your next solution, because every vector database is built a little different, right? You want to really find the one that suits your scenario the best. And also you have to consider your technology stack, right? And what kind of languages, right? What kind of ecosystem you want, right? You want it in Python, in Java, or even SQL, right? And that's. And also you want to consider, if you want to self-host, right? Self-host something that's open source, or you want to keep going for something that's cloud managed but proprietary, right? And or you want to go for something that's cloud managed and open core, right? So in case another Rockset happens, you have, you don't really get locked in, right? And here are some examples. There's just so many of them. It's impossible to actually like go through each one of them one by one. And those are some dedicated vector databases, for those really scalable, just tons of vectors, and some of them support GPU, right? And also there are some SQL databases that has vector similarity search capabilities, right? The ones in here are not the complete list. And the ones in here supports ANN, so approximate nearest neighborhood search. But if your use case is something like, a very simple RAG, just tens of thousands of vectors and not that high of a QPS, you probably don't even need ANN, right? You probably don't even need that approximate. You probably don't even need vector index. You just find a fast database that can like an array, and you compare two arrays, do a full exhaustive search, and that's probably fast enough for you, right? So definitely really consider a use case before you actually go research for different solutions, because there's so many of them and they're very different. Okay, and then let's go talk about real-time analytics, right? And this is before Rockset was started talking about AI and search, vector search, and those kind of applications. And this is their core scenario before the LLM period, right? And they were a good, they're still a good real-time analytics solution, right? For a few reasons, right? And first, how they store data. By nature, they support streaming in real time data, right? With data upserts, with mutable data, right? With data freshness in in the low seconds with mutable data, and that's pretty impressive for a real time analytics solution, right? And I really have to give it to them for their ingestion pipeline, or their ingestion tool set. They have a great change that CDC support for, like, say, Mongo or DynamoDB, right? And the real-time ingest ecosystem is really well built, right? And third, they're able to run pretty fast aggregated queries, right? And also, thanks to the variety of the indexes they have, Rockset is really able to support a really wide range of queries, from OLAP to text search to very fast point queries, from their role store, right? So these are the good. So when you find your next solution, try to match those, right? Keep the experience the same. But Rockset does come with some challenges as well, right? And those challenges, some of them you probably already know, but I'm gonna go through them. And moving off of Rockset, depending on your scenario, is probably more of a good thing than bad, right? More of an opportunity than a disaster, right? So first challenge is indexes. Indexes is what make Rockset special, right? It's able to run that many different kind of workloads with incredible performance, right? But it really does blow up storage, especially when compared to kind of like a data warehouse, right? Because it stores in the document and build just so many different kind of indexes. So this is a test I did around like 2 years ago. I cannot really do a new one because they don't allow new registrations anymore. But this is the line order table from the SSB benchmark test, right? This originally it should be a 50, I think 50 to 60 gigs in uncompressed text file, right? But after ingesting into Rockset, it becomes almost 600 gigs. So almost a 10x blow up, right? And also on S3, it's not that bad, but they actually require everything to be in hot storage for it to get good performance, and they charge a lot for hot storage, and this can be very expensive even you have not that big of a data, right? This 10x probably already look pretty challenging, but when you compare it to another data warehouse, it becomes more severe. So data warehouses or like OLAP databases typically store data in a columnar format, right? Instead of storing everything by row, it stores everything by column. And by column, it's just so much easier to get better compression ratio out of, because everything in one column, they're similar, right? And here is an example. So this is StarRocks. It's a real-time data warehouse, columnar storage. And this line order table, the same exact table with the same exact number of rows, is only 14 gigs in StarRocks, right? When compared to 600 gigs. And this is not even the most kind of severe scenario, because, right, the most severe scenario I would say is something like a log, right? I've seen in the field that hundreds of terabytes of log can be compressed to gigs, because there's so many repetitions in those records, right? So and this is really a challenge from Rockset users, when we talk to. Okay, so the second is actually joins. So before we actually talk about joins, here let's first go through some join related concepts to get out before we actually dive into this. So join, there are different things for join, right? There are join types. They're logical representation of a view, right? It represents what the result set looks like, right? You have inner joins, outer joins, cross joins, semi joins, and all those different kinds of joins, right? And there's the logical view. And then you have join algorithms, right? You hear a lot about hash join, parallel hash join, merge sort join, and those are how a join is executed on a single node, right? On a single node, how a join is calculated, is computed, right? But and then you have join strategies, right? Join strategy is basically how you would run a join if you have more than one node, right? You have single instance join, just join a single instance, co-located join. You distribute the data on your join key, right? So you don't move data around. You have a broadcast join where you broadcast a smaller table to all of the nodes and then do the join. And you have shuffle join, basically is you reshuffle the data, right, based on the key, and then run the join distributedly, right? So the actual important thing here is, so first ask yourself a question: does your workload fit in one node? If the answer is no, join strategy is definitely the one you want to focus on, right? It doesn't really matter how a join is executed, on a single node, or what the join looks like. Join strategy is what you really should focus on, right? Rockset does claim that they are able to run all sorts of join algorithms, but they don't really talk about join strategy, and this is what the challenging part is, right? Next slide. Okay, so denormalization versus on the fly join. Rockset does support full join index. The first one we talk about, a logical view of a join, and it supports all kinds of join algorithms, but it doesn't support any distributed join, no shuffle, right? No data shuffling. So here are two kind of popular higher level compute architectures that data warehouses use to do computation, right? So first is scatter gather. Basically, you would have different nodes, and you have a main node, right? And you distribute the task to each one of the nodes, and each one of the nodes compute the result with the data they have, right? And then send it back to the main node and do the final calculation, right? And this really easily bottlenecks on a single node, right? It's not suitable for joins, and it's not suitable for high cardinality aggregations at scale, right? Let's just say for a join setting, right? Scatter gather systems, the big difference between scatter gather and MPP, I'm going to talk about later, is that it doesn't really have a shuffle operator. It cannot really reshuffle data during query execution, right? So once the query already started, what you have in the node is what you have, right? So let's say in a join setting, right, distributed join setting, you do a broadcast join, and this is probably the only thing that scatter gather system can do in terms of distributed joins. Basically, you send all of your smaller table, right, your left table to all of the nodes that are there. But if your left table is too big, it does not fit in your nodes. It doesn't work, right? So data shuffling is absolutely required if you want to run scalable join operations. And this is where MPP comes in, right? So with the ability to reshuffle data during query execution, right, it really streamlines the query execution process with absolutely zero wait time, right? And then it ensures scalability and performance. And then you run everything in memory, or you shuffle between the memories of each node, right? It's great for sub-second joins and aggregation at scale, right? And this MPP with in-memory data shuffling is the way of running joins at scale, right? And a Rockset is based on a scatter gather kind of compute architecture, and this is why it cannot really run join at a scale with big data sets, with complex joins and high cardinality aggregations, right? And so not being able to run join at scale, so Rockset users we see a lot is that they're forced to go into denormalization mode, right? You have normalization, which is from flat tables to your multi-table schema. Your denormalization is, from your multi-table schema back to a single table flat table schema, right? Normalization has been, a good practice since the invention of relational database systems, right? In the 70s, eliminates redundant data. It simplifies the query process, right? It improves workflow. It's just overall just so much better, right? And we're going back to this denormalization thing because a lot of the real-time OLAP databases or data warehouses just cannot run joins at scale, right? And denormalization is actually pretty harmful. You get rid of the join, but at what cost? So this is an example. So let's say you have a dimension table here, like a customer table here, and you then have a detail table, your right table, here, right? Both of them has a customer ID, and customer ID is the primary key on the left table, right? And because you want to run some queries that from those two tables, and maybe a BI dashboard, right? But you're using a data warehouse that doesn't really do join at scale, right? So what are your options? So you have to do a denormalization, right? You denormalize, you pre-join the two table into a big flat table, and you run the queries, and it's all good, right? But one day your security team comes over and say, hey, your customer name column cannot really be, the names, you have to somehow mask it, right? Let's see how this plays out, right? So not only you have to alter, rewrite the whole column for the dimension dimension table, and this is okay, right? It's probably not that big of a table, but you have to rewrite everything in the denormalized flat table as well, right? And the number of record in this table is not really comparable to the dimensional table, right? And rewriting this whole column takes a very long time, right? Long enough that denormalization locks your data into a single view format. It doesn't really. Once you do this, you don't really have the flexibility anymore, to quickly adopt to any business change that really fast, right? I've seen customers, they were on another solution, right? It was complaining, I built a metrics platform, and just because I have denormalization pipelines, changing a metric can take, hours or up to days. It's just not really acceptable for them, right? And denormalization not only makes your schema rigid, it also makes a very complex real-time data pipeline, right? Because everything is in real time, right? You want to do denormalization if you want to do it with kind of like a batch tool like Spark, it doesn't really work because it cannot really keep up with the short intervals of the ingestions or how fast the data are being processed batch by batch, right? You have to go for a stream processing tool and write stateful stream processing jobs. And that is really expensive and complex and requires actual coding, and it's really error prone. It takes a lot of resource as well, right? So the stream processing is very difficult to do. And actually we have users, they build customer facing like applications, but it's not real time. Why? Because they were on a solution that cannot do join on the fly, right? And this whole process just so much work and so complex for them to implement. It's just not worth it to go real time. And this is the whole denormalization versus on the fly join challenge is what we believe that the biggest hinder to wider adoption for real-time analytics, right? Okay, so now let's talk about we talked about the challenges, and now we start talking about some alternatives for Rockset's real-time analytics workloads, right? So first is Apache Druid. Apache Druid was open source in, I think, 2012, right? And I remember that time. I think that was the first time that on the fly aggregation is actually seemed possible at the time, right? It was really fast and at the time, and it was great, yeah. So it has a lot of pros. So it's able to do real-time pre-aggregations, through rollup, right? And that really works. So if your scenario is something like a report or a dashboard where your queries follows a certain pattern you already know, right? You already have those columns that you're gonna need to aggregate on. You can build rollups on, and Druid is still great, for those use cases, right? And Druid might be something to consider if you have a use case just like that. And also, it's a very mature product, been around forever, and it's very stable, right? But it does have a few challenges. Talk about Apache Druid, right? First, it does not support real-time data upserts at all, right? So your data has to be append only. And also, it requires denormalization because join does not really work in Druid at all, right? And third is Apache Druid is written in Java, so raw performance is quite challenging. It's quite a bit slower than some more modern solutions we have now today. And also, although it has a deep storage, you can persist your data, but the data has to be loaded into your local nodes for query. So it doesn't. So it doesn't really. Yeah, it separates storage and compute, but it doesn't really, right? Because you cannot really scale, on demand, right? Because all of the data needs to be loaded, to be able to query, right? And this is Apache Druid and ClickHouse, right? And ClickHouse was open source, I think, like 4 years or 3-4 years after Apache Druid. I remember that time too. And ClickHouse is actually, say, on the fly aggregations is possible now, right? It's very doable now. It's Columnar store, C++, SIMD, right? Great aggregated query performance, right? It has really good compression because this is what its original scenario is log analysis, right? Has great compression and great aggregated query performance. Plus, its full text search capabilities is really good for log analysis. If your scenario is something like this, ClickHouse might be a great choice for you. And it has a very open community. It has functions that are contributed by so many different users. So if you're using ClickHouse, you need a function, it's probably there. If it's not there, you can contribute. It's a very open community, just like StarRocks, right? But it does come with support data upserts, but it relies on read. So which means that when you write your updates or your ingest into a merge on read table, into a merge tree table for ClickHouse, it writes into different versions. And then there's a compaction job that try to merge those different versions into one, right? And that can heavily affect query performance because by itself is expensive, and also you cannot really do predicate pushdown, right? And not only make your query slow, but it makes it incredibly unpredictable, right? Especially in a real-time setting. So ClickHouse, yes, it can do upserts or mutable data, but it doesn't really work that well in a real-time setting, merge on read, right? And also requires denormalization, right? It's also scatter gather. When you have a lot of data, join is just not possible with ClickHouse. So you have to build your denormalization pipelines, even for real-time analytics, right? And then we have StarRocks, right? StarRocks is, in my opinion, a good choice, for your Rockset alternative. StarRocks is a Linux Foundation open source real-time data warehouse, right? It's able to perform second-level data freshness with mutable data, right, directly on your columnar storage. And I'm going to talk about how it's able to do that in the next few slides. And also, it has MPP architecture with in-memory data shuffling. Right? You can run really scalable on-the-fly join queries with absolutely no denormalization required, for your real-time analytics workload. Right? Also has a shared data architecture, which means storage and compute separated architecture. So your data, if you're using StarRocks, your data is persisted in a cloud object storage. And StarRocks is still able to directly query that data in your cloud object storage so you can scale, on demand. And CN nodes, which is the execution nodes, the muscle, right? It caches data in its local storage, right? For query acceleration, right? So you get the best of both worlds, right? You get the best possible performance, and also you get the flexibility of, of the cloud, right? The ability to dynamically scale and to store your data on the cloud object storage, to persist your data on the cloud object storage, which is a lot more cost effective and a lot more scalable. Infinite storage, right? At a very cheap cost. And also StarRocks supports standard SQL, MySQL protocol, so you can keep all of the tools you love, as long as it speaks standard SQL, it should work out of the box. And also it has a very fast growing open source community, right? The thing I trust StarRocks the most is its multi-table query performance, really fast joins. So this is a really interesting benchmark test between StarRocks, ClickHouse, and Apache Druid. This is the SSB benchmark test. So resemble those queries like for a BI tool, right? Not too complex, but with aggregations and joins, right? And everything you on the right you see with a flat is a um, variant of the original SSB benchmark test. The original benchmark test is a multi-table test, but the flat version is created by the folks at ClickHouse, right? They basically did a denormalization of all of the tables and only run the on-the-fly aggregations, but not on-the-fly join, right? And this is a flat. You can see that StarRocks is faster than ClickHouse, a little bit faster than ClickHouse, and a lot faster than Druid, right? But the key thing here is with StarRocks, MPP architecture and its cost-based optimizer, and all of the optimizations we did over the last, 2-3 years, it's able to run the original SSB test with joins faster than Apache Druid's single table performance and almost as fast as ClickHouse single table performance, right? And join is probably one of the most expensive thing you can write with your SQL. And this, by itself, it says, dishing denormalization is actually possible, with a well-tuned system, right? And real-time upserts on Columnar store. How StarRocks does it? How does it match Rockset's capability with only a columnar storage? Only columnar storage, with fraction of the storage that's required compared to Rockset, and still get this kind of capability, right? It doesn't use a traditional merge on read, what we talked about in the previous slides, where it can hammer your query performance because the merge operation is expensive, right? Actually, StarRocks invented its own delete and insert strategy for real-time data upserts. How does it work? Is that when you write your data, it translates into inserts and deletes, right? And deletes are marked deletes. And so when your data is written, all of the inserts are inserts, and the deletes, you mark the deletes during the data ingestion process, right? Synchronously. And then you StarRocks filter those deleted rows at query time, right? Just on the right-hand side, all of the grays are the marked deletes, generate a delete bitmap for query time execution to filter, right? And to accelerate this mark delete process, StarRocks implemented a primary key index where it maps your primary key column to wherever that piece of data is stored on the storage, right? So this is with the index, it's a very fast and efficient process, and everything is done synchronously during data ingestion, right? So by doing this, there's no more merge operation. So you get the best possible query performance, right? And because of the primary key, the existence of primary key, this can be done very cost effectively, very cheaply, right? And you can actually do second level data upserts. So sub 10 second level data upserts directly on your columnar storage. A fraction of the storage required, when compared to a solution like Rockset, right? That requires a role-oriented storage. So in the end, I want to show a use case from Airbnb. I think everybody here already know what Airbnb does, right? And this is their fraud detection use case, right? To protect their user and platform's interests, their data scientists have to, detect those violations fast enough, to reduce their potential losses and to protect their tenants and their customers and to protect their brand, right? That requires system with the following capabilities. So first, it has to be able to do real time, right? Second level data freshness, and also it has to support mutable data because mutable data is everywhere with Airbnb, with their Airbnb, so their hotel statuses, with their transactions, everything is mutable, right? This is absolutely must for them, right? And also they run really complex queries, on top of their data, right? They have to be able to run ad hoc like queries, with second level latency, right? with joins and aggregations done on the fly, right? And they don't want to build a lot of heavy pre-computation pipelines, right? Because their schema change too, right? So second level latency, and this paired with the data freshness, there is a certain time constraint they need, to detect those violations in time, right? And then they use StarRocks, right? They stream data from Kafka directly into StarRocks primary key table, which is talk about the delete and insert table, right? And this primary key table itself, can ensure second level data freshness, right? And for their complex queries, because they're using primary key table, it doesn't really affect query performance, so they can maintain a very low latency queries, right? And also it's MPP architecture, so it can run all of the crazy joins and high cardinality aggregations on the fly and still get great performance, right? And this whole thing ensures that they can identify those fraudulent activities in time, right? We do have a case study, Airbnb. Just Google CelerData Airbnb, you can find it, or StarRocks Airbnb, you can find it, right? And this is actually all I have. I hope it was helpful, for you guys to find your home for your next Rockset workload. If you're interested in StarRocks, CelerData actually has a managed version of StarRocks, enterprise managed version of StarRocks called CelerData Cloud, right? You can register today, cloud.celedata.com, and get your 30-day free trial. And also, if you're not ready, always join the Slack channel. It's a really fast-growing community with a lot of users talking about real-time analytics and vector databases and all kinds of really fun things, right? Thank you. Is there any question? If you have any question, now would be the time to ask. Okay, I do have one question from okay, let me read it. So how does StarRocks compare to Impala? Okay. So yeah. The main difference is vectorization, right? StarRocks is vectorized, so basically means you're able to StarRocks is able to in memory everything in columnar, right? So process everything in memory by batch, right? And it's also C++. So for every CPU cycle, it's able to process multiple data points of data, right? And pair it up with columnar storage, and this is why gets its performance benefits. Any other questions? Okay, I think this is it. Thank you guys for joining, for tuning in. If you have any more questions, you can raise them in the Slack channel. You can direct message me too. Happy to address any follow-up question you might have. Thank you guys for tuning in. We're going to see you guys again next time. Thank you.